Hello, I'm Michalis Famelis, and I'm gonna be talking to you about modeling different kinds of uncertainty. I'm a professor at the University of Montreal, and this is work that I did with Muna Dawadi, my PhD student, as well as colleagues from Smith College, Kate Spencer, Megan Varnum, Malaysia Group. So, um, in my academic work so far, starting from basically 2010, I've been working on this idea of uncertainty about design decisions. So, to give you a little bit of an example, imagine we're trying to create a MDENet meta model. So we go to the Atlas MetaModel Zoo, we look at many examples of meta models, and we decide that, at the very least, we need to have concepts for places and transitions. But of course, the zoo contains all sorts of different kinds of meta models, so we have some real design decisions to make here. Do we want to represent things like tokens? Should we model arcs as things between place and transition nodes? There's some very deep design decisions that we can make, and it's not clear how these decisions should be made. It's not clear what they should be. So this kind of uncertainty I've been calling design time uncertainty. Uncertainty is a very broad context. It means many things to many people. In my work, I've used it to mean the modeler's lack of information about how to design the model. There's been many approaches to deal with this, such as ignore it, pay the price, or walk around it, under-specify using formal notations, things like that. One approach that's been used by myself as well as colleagues in the modeling community is this idea of modeling this uncertainty and managing it. So in the spectrum of different kinds of uncertainties, all the way from complete deterministic certainty about a phenomenon, all the way down to total ignorance, I don't even know that I don't know things. We have been looking at design time uncertainty as a set of known possibilities. So we know what the possibilities are, but we don't know, what are there. We don't know which one to pick. So, in my work, I've built a methodology about how to do this. This is called the Design Time Uncertainty Management Model, the D2 model. It's in my PhD thesis and in a associate paper. And what I'm proposing there is to represent this uncertainty in a partial model. Work with this partial model using all sorts of formal techniques so that we maintain the uncertainty and we don't lose it, and at the end resolve it systematically and with nice guarantees. A partial model looks like this. It has a graphical part and also a propositional formula, and I've played with different ways of representing this, including something looks like a little bit like a feature model, but not exactly, where you can say what are the points of uncertainty about the model. All of these things I've done, none of them were quite right, I think, but some very interesting lessons were learned. So since I became a professor 5 years ago, I've been thinking about this problem from different perspectives. One of the most recent iterations about this has been centered around this Druid framework that I'm going to talk to you about now. So what we did is we created a modeling language, because that's what you do, right? So we came up with a meta model called Druid, Design Requirements Uncertainty IDE. There's no IDE yet, but there's a language. What we did here is we put together, like a druid puts stuff in a cauldron and cooks a potion. We cooked this meta model using ideas from all sorts of sources. An uncertainty taxonomy that from Walker and et al. That gives us the idea of levels of uncertainty. The U model from Zhang et al. That introduced things like indeterminacy, source, and nature. The Doppler framework that talks about decisions, questions, decision types, dependencies. The decision modeling notation from the OMG that introduced things like information requirements, and a decision needs information from another decision to be made, as well as partiality from the work of Saleh and others that introduce things like low-level partiality, how to represent uncertainty at a low level, such that it would allow things like refinement, concretization, and so on. So with our modeling language, with Druid, things that we can do is you can start, in my example of a PetroNet, right? You can start with your PetroNet, and then you can document the things that you're uncertain about. Then you can localize and say, the thing that I'm uncertain about has to do with this part of the model. then you can do some work to elicit some concrete decisions that allow you to operationalize the uncertainty at the high level, at the low level of the model using particular partiality mechanisms. DREED also allows to express different kinds of relationships between decisions and to store all sorts of metadata, such as the source of uncertainty, its nature, and so on. So we built this meta model, and then we wanted to see if it is useful. So in this work, we did this case study centered around the COVID-19 pandemic. A little caveat here is this was at the very beginning of the pandemic, so some of the questions that you will see in this case study will sound a bit naive, but you have to remember we were doing this all at the beginning of the pandemic, in early 2020. So in this case study, what are we doing? We're taking the point of view of a persona called Emma. Emma is a Quebec resident who wants to decide how to safely get dinner in the middle of a pandemic. So the options that she has, she can cook at home or she can get takeout. But she's worried whether she's worried about social distancing. She wants to do her part, but also wants to support local businesses. To help her decide, we take the point of view of a person developing developing an app to help people like Emma, and so therefore we're doing early requirements, and we're trying to model, on the one hand, our persona's goals and intentions using Tropos, which is a goal modeling notation, as well as epidemiological data about the COVID-19 pandemic that were produced in Quebec from researchers doing research in COVID using an epidemiological model, which in this case is a Bayesian network. So we represented these models using MDE concepts, and we tried to connect them, and then to help Emma connect her own personal decisions on the one hand with their social impact based on the best available science at the time. So we were trying to understand whether DREED can help do all of this. Okay, so we built models like this to dive into some more specifics. So here you have the Tropos model, the goal model, and here all the stuff around is uncertainty. So on the Tropos side, you have goals like have dinner. You can do it by cooking at home or getting takeout. If you cook at home, that helps the goal of practicing social distancing. Get takeout can hurt it. And then, for example, if you practice social distancing, that can help not get or transmit COVID. This kind of model allows us to model the uncertainty that exists in Emma's predicament. The uncertainty, what should Emma do? Should she do this or should she do that? So it's uncertainty sort of in the requirements. But then with DREED, we were able to model something different. We were able to model the uncertainty that the app developer has about what exactly those requirements are and how the scenario is structured, right? So in this case, we have the uncertainty. I don't know exactly what the relationship is between practicing social distancing and not getting transmitted COVID. Remember, this is the beginning of the pandemic. And based on this uncertainty, I don't know whether I should add this arrow helps there or not. Like, is practicing social distancing actually helping not getting COVID? Okay. So already you can see that there's two different kinds of uncertainty. You have uncertainty about the scenarios and what the app would be doing and how Emma should navigate it. And on the other hand, you have the uncertainty that has to do with how the scenarios are structured and what they contain. On the other end, we have the epidemiological model. So we used a model that was published in 2020 by the health authorities in Quebec. Basically, what you have here is a Bayesian network. It has transitions like this. So, for example, you have variables such as percentage of the population that's hospitalized and percentage that is recovered, and then you have a transition that has there's a probability table. So you have, if you're hospitalized, you have 98% chance of recovering, for example. So here on this end, in the epidemiological model, what we're actually modeling is we're modeling the uncertainty that is inherent in the pandemic. We're modeling the stochastic aspects of this natural phenomenon, right? So this Bayesian network is really good at modeling exactly the kind of uncertainty about how COVID exactly works. This probabilities right there express this information. On our end, on the modeler uncertainty, the design uncertainty, we can say things like, I'm not sure exactly for this particular app that I'm building, I don't know what exactly to emphasize. Do I want to be talking about hospitalizations to Emma, right? So it might not be clear from the point of view of our app developer what variables should be relevant for this scenario. And therefore, you have uncertainty about that, and you can have decisions. Should we model recovery, for example, as a variable, right? So you have uncertainty about how exactly to build your Bayesian model, what you should keep in, what you should keep out for your particular scenario. This becomes a little bit more obvious in cases like this, where we were trying to model things that were not actually part of the epidemiological model. So, for example, what is the effect of respecting preventing measures to being exposed to COVID? So the report, the publicly available report at the time that we were doing it, did not contain any information about that. So obviously there's an uncertainty about what are the probabilities on this transition, right? So with Druid, we were able to explain why actually our model is incomplete, or if we really wanted, we could have added some, random provisional values there, like 50-50, for example, probability or something like that. So we could document that on the Druid side. Again, on the Bayesian side, we are representing uncertainty about the phenomenon itself, but here we can represent the uncertainty about the Bayesian model. Finally, the final step was putting all of these things together, right? So this becomes a big, massive graph that is completely unreadable, but you have things like this, right? So you have, on the Tropos side, you have the get takeout task, and on the Bayesian network side, you have the respect preventive measures, right? So there is a decision. Should you consider that getting takeout is actually to be considered a preventive measure? You can start asking these kinds of questions. And so you can have uncertainty on the mapping between the two models. And then you can have things like uncertainties on the one end affecting uncertainties on the other end. So if you don't know exactly how the probabilities of the effect of respecting preventing measures to being exposed, this uncertainty here, this could inform how exactly you're going to model your scenario on the Tropos side by saying, practicing social distancing helps or not getting COVID. So this allows us again to express uncertainty about the mapping, but also to trace and relate uncertainties on the two different ends of our models. So, some lessons learned. It was useful for us to model uncertainty within the model, identify the sources of uncertainty, and document all of that. It was especially interesting to do this intermodal, across models mapping, to describe the uncertainty in the mapping and to map, match, and merge the different uncertainties. And the thing that when it comes to answering our research question, how can Druid help here? It actually helped us a lot develop this in our case study. But the biggest lesson learned that we had here was that different types of uncertainty need different modeling approaches, different modeling languages, and different treatments. You have different phenomena that are uncertain here. You have on the one end the uncertainty inherent in a stochastic phenomena that's best described with the Bayesian network. You have the uncertainty that has to do with the scenarios of inner requirements analysis that is described best in Tropos, and then you have the uncertainty that has to do with building all those things and mapping them and so on. So that we were using Druid for that. So the big message, I guess, to give you here is that we need a sort of separation of modeling concerns. It's very useful to decouple the different kinds of uncertainties that you have and use the appropriate modeling formalism for that. So in our next steps, we're trying to evolve Druid. We want to give it formal semantics, and we have been investigating a little bit the idea of rational reconstruction and using intelligent assistance for that. So with that, I thank you very much. Thank you for your attention, and I look forward to having a very nice discussion.